Hi everyone. Okay, let's have a quick look at this question. Pause it if you want to have a go at it, otherwise continue watching. A block B has a mass of 1 kg on a smooth plane inclined at 35 degrees to the horizontal. One end of the light's inextensible string is attached to B and it runs from B up slope parallel to the line greatest slope to the plane to a smooth peg. The other end of the string is attached to a particle P of mass 2 kg that hangs vertically below a peg exactly 1 meter from the floor. Okay, so let's just draw this diagram here before we start anything. Let's just say this is the horizontal, this is the plane. The plane is running at 35 degrees. Okay, so we've got this block B. I'm just going to put this block here. Has a mass of 1 kg, so that just the weight just drops as 1g, just g. So that's coming down here. Contact force with this one is R in here, and this runs perpendicular to the slope, so that runs down with, that's 35 same angle, so that's going to be 30 let's first put g times cos 35. That's running downwards, and you've got running down the slope here, going that way, it's going to be g sine 35. Okay, so we've got those so far. Now we've got another scenario here. So we've got the 1 kg sorted, smooth, there's no friction, 35%. Now this light and extensible string is attached to B. It runs from B parallel to the slope, so I'm just going to run this string running up this slope. Let's just do a bit higher up here so it doesn't intervene with these numbers here, and it runs through a peg, so point P, so parallel to the slope, greatest slope from a smooth peg, so there's the peg, so it runs through here. The other end is attached to a particle P, so that's my B. This is my particle P. Okay, and this has a mass of 2 kg that hangs vertically below the peg 1 meter from the floor. So this is running down here, and this has a mass of 2 kg, so that's 2g dropping downwards. But that is 1 meter away from the ground level. Okay, let me just double check I've read everything, got everything sorted here. That's 2g. Right, the only thing is tension. So if that's one more thing, it's inclined, lighting extensible string is attached to be the greatest slope of the peg, so there's attached to that, and P, particle P of mass 2 kg hangs. So you have got tension in here, so that would run freely, so that's holding that up. You've got the tension, and you got the tension there. So we don't know whether it's pulling it or holding it, which way it goes. All we know that is 2g dropping down that way. Okay, now given that's 1g, you would assume the motion to be coming this way. Well, I'll have a look at that. So you'll expect the motion, the acceleration to run this way, since that's 2g is heavier than that, and it should be pulling it. Okay, so one more go at reading it. A block B of mass 1 kg lies on a smooth plane, 35, we've done that. One end of the light inextensible string is attached to B, we've done that. It runs P upslope parallel to the line. We've done that. Greatest slope to the plane. The other end of the string is attached to particle P. We've done that, of mass 2 kg, hangs vertically below the peg, exactly 1 meter from the ground. So it's 1 meter off the ground. Okay, we've got all that information. With this information now, we just need to look at this diagram. We don't need to read that again. Everything is there that we need. The system is released from rest. So when it's released from rest, you know that initial velocity is going to give me 0. So it's released from rest. Find the acceleration of B up the slope. So we're going to now find, as I assumed correctly, that the acceleration is going to be up the slope, as this is heavier, so it's going to be pulling it down. Okay, so let's do this one. Before we start acceleration, we know that force by Newton's second law is mass times acceleration. So we're going to use this, and we know that the forces which are acting on here, so what is going against it and what is going up. So the tension is pulling it up, and what's going against it is this slope and the weight of it. So let's just set it up here. So we've got one equation. Equation 1 will be the tension pulling it up, and what's going against it is going to be this weight of the slope. So that's going to be G sine 35. Okay, that's the only thing that's going. So that's pulling it, and that's going. There's no friction, and that will equal mass. Now the mass of that particle B, the block B, is 1, so that's just going to be 1A, just A. Okay, now we get a second equation which comes along here, which happens vertically. So this one was running down along the slope. Equation 2, what we got here is this is running down, so what's leading here is this weight, 2G. Okay, so you've got 2G, and what's opposing it from dropping freely is the tension, minus T. And that's going to equal 2A, because the weight of this particle P is 2 kg, is 2 times acceleration. Note, because it's a single string here, no drops, so the acceleration in each case is the same. Okay, so A is the same. So what we can do is now we can get rid of the tension, because we need to find only the acceleration of B. So we can add these two together, and by doing that we'll get 2G minus G sine 35 equal to 3A. Hence the tensions will cancel out. T minus T will go. So we'll just divide that by 3 and get acceleration is equal to, actually you can just put that all in your calculator now. Let me just rewrite this a bit better. Just trying to save as much space as I can. So therefore in this case acceleration will be, if I type in my calculator, 2 times 9.8 minus 9.8 times sine 35 over 3. That will give me, to three similar figures, acceleration 4 point, now I've got 6596, so that will be 66 meters per second Okay, so that's our first part. Just have a look at that, be careful, you got everything, all that information runs from there. Okay, so if I just put a different color and separate this part B. So let's look at B now. Okay, so first one, the acceleration of that up the slope was 4.66 meters per second Happy with that. Now it goes here, when P hits the floor, the string breaks. So P is going to hit the floor. So that's gone up here, gone there, that's hit the floor. And the string breaks. So there's no more tension. That string breaks. Actually, no more tension. Okay, when the string breaks. Assuming that the initial distance between the block and the peg is sufficiently, so the block and the peg is sufficiently great that the block will not reach the peg. Okay. Find the total distance traveled by the block when it instantaneously passes through its initial position. So what we're looking at, so this is initial position. This is a meter off. Okay, so it's gonna come down 1 meter, and with that 1 meter, we're gonna assume there's gonna be some distance that is gonna still as it's going at a certain speed, it's gonna still continue to climb up, and then it will go down that same distance, and then the 1 meter it traveled to go through there. Okay, so that's what we're going to try to have a look at. So first of all, we need to, because it's all these masses acting on this, it's just constant, so we got constant acceleration. Okay, there's no extra mass, so the forces are constant, so acceleration is going to be constant, so we can use that. So in our first instance, when it travels 1 meter, so let's just put that here. So the first one, we know that it's traveled 1 meter. Okay, and then at that 1 meter, what can we do is we can we know what the acceleration is up the slope, so we can put that down. Acceleration is 4.66. So what we need to do is I want to find, so it's gone from there, we need to find its speed. So initial speed was 0. I want to find its final speed, which will then become its initial speed, yeah, and that's after it's traveled through 1 meter. Okay, yeah, let's do that. So we've got SUVA, so it's here. I'm really sorry, I'm trying to save some space so that I can get this sorted. So we've got V squared minus U squared equals 2AS. Now we want to find what V squared is, the final speed. Take away 0 squared equals 2 times 4.66, and S is 1. So if I put all that in a calculator and square root it, so I'm just going to quickly do that all in one go. So we get 2 times 4.66 times 1 equals that. So we get, on my calculator I've got 9.32. So V is going to be 9.32 square rooted, which will be square root that, which will give me 3.0. Again, to 3 single figures, 5, I'm going to call that. So when it hits, before it breaks, when the tension hits, when P hits the ground, it's traveling, the particle block B is traveling at that speed. Okay, I just wanted to put that into there. So now, second scenario. So we've gone through that, it's traveled through 1 meter. Now this one, we need to find how much distance it travels. Okay, find total distance travel. Yeah. So we need to find what distance that will travel when the initial speed is this final speed, 3.05, and my final speed is going to be 0 when it comes to a stop, then it starts traveling back. So acceleration, now yeah, acceleration would have changed because there's no more tension, so I'll come back to that acceleration and timing we don't have, so we can leave that. So once we've got the acceleration, we can then find that distance. Now note that when it's being dragged up, when it hits the floor, the tension breaks. So therefore the only force that's going against is actually this pull going downwards. So it's going to be acceleration is going to be minus, so we're still using that formula, force equals mass times acceleration, but this will be a minus g sine 35, because that's the only force going down, opposing motion, okay, going down, and that's going to be the mass of that particle of the block is just 1, so that's 1a. So actually the acceleration is just going to be minus g sine 35 because there's no tension there. So when we look at here, this is snapped, so acceleration is just minus g sine 35. So if I put that down, 9.8 times sine 35, my acceleration is going to be minus 5.62 to freezing figures. So that's going to be my acceleration slowing this block B down. Okay, so we need to find what that distance it travels whilst this is slowing it down when it comes to a stop. So we've got SUVA. So again we got the formula V squared minus U squared equals 2AS, and then I know that V is 0 minus U is 3.05 squared, and divided by 2 times, now the acceleration is minus 5.62, and that will give me the displacement. So two negatives will cancel each other out, so if I just put 3.05 squared over 2 times 5.62, that's going to give me a displacement of 0.82 to freezing versus 8 meters. Now let's work out the total. He wants the total distance. Okay, total distance traveled by the block. So what will happen? Let's just work this out. So total distance first, it traveled 1 meter. Then when the tension snapped, it went up before it came to an instantaneous stop, and it traveled 0.8 to 8 meters. So then it must travel all the way back the same distance here. Okay, so it's gone there, and it says here when it instantaneously passes through its initial position, it's traveled all that up, so it must travel the same distance on. So basically all this distance is going to be times by 2. So add 1 equals times 2 will give me a total distance of 3 point, now it says 6552, so I'm just going to call it 3.66 meters. It's going to be total distance travel. Okay, it's a bit of a tricky one, but just pay attention to what happens here, because the motion when that's coming up, it's actually got some speed it's coming up with. As that hits the ground, the tension breaks, but that force is still, the speed is still making it go up, and it's actually this force against it, this deceleration, which is slowing it down, will start making the particle slow down. It's still traveling, but it's traveling slowly. Then it comes to a stop, and that's 1 meter plus that distance. It takes almost another meter before it comes to a stop, and we assume it doesn't hit the peg, and then it starts coming back down. So that's what we wanted, assuming that the initial distance between the block and the peg is sufficiently great that the block will not reach the peg, find the total distance travelled by the block when it instantly passes through its initial position. So go for its initial position again. Once it's gone through there, come back. Okay, happy with that.